Hi everyone, in this video we're going to go through the difference between an arithmetic sequence and a geometric sequence. So basically with sequences, the two ones that you will look at in general maths are arithmetic and geometric. And if you've already done Unit 1 and 2 or even in Year 10, you should be familiar with them, but I will just recap them in this video just in case you have forgotten. So arithmetic sequence, as you can see, we're adding a common difference, or we could be subtracting as well. So a sequence is just a series of numbers. So you can see here we've got, let me just grab my highlighter. We've got 1, 3, 5, 7, 9, and we could keep going because we can clearly see the pattern is we're adding 2 each time. So that's what an arithmetic sequence is. So you can have an increasing arithmetic sequence where you're going up each time. So this one here, we're going up by 4. Or you could have a decreasing arithmetic sequence. So we're going down by 3 each time. But your common difference is if it's positive, it's going up. If it's negative, it's going down. So your common difference can be positive or negative. But basically just think, all right, we're either going up by the same amount or going down by the same amount. All right, so if we just had a look at the graph of a arithmetic sequence, it would be a straight line. It would be linear because we're going up by the same amount each time. Or if it was going down, it would be like that. All right, and if it's going up, we call that linear growth or arithmetic growth. And if it's going down, linear decay. Basically, what we have here, if we were to form a straight line, you would have a line y equals mx plus c, where m is your gradient. So your common difference is also just your gradient in a straight line. Those examples are pretty straightforward. Now in general maths, the main things that you need to realize are the recurrence relation and your rule. Okay, so with a recurrence relation, it may seem like a little bit more complicated because we're introducing letters and some numbers and the letter N. You're like, what does this actually mean? It's basically the only thing that will change is your initial value and your common difference. And obviously if we were going down, it would be a minus like it is here for linear decay. So with your recurrence relation, you're always going to have V0 equals and then whatever your initial value is, and then you're going to have Vn plus 1 equals Vn, and then your common difference. So if we just have a look at the two examples above, here I would have my initial value, which is V0, is 20. All right, we're starting at 0, and then my recurrence relation, we have the Vn plus 1, so that will be present for every recurrence relation equals, and then we've got Vn, and then our common difference. So for this example, it's 2, so it's going to be plus 2. For the second example, we're still starting at 0, so V0 is 20, then we still have Vn plus 1, Vn, all right, so remember that's common to every recurrence relation, but this time our common difference is minus 2. All right, we're going down by 2 each time. Now you might think, oh, that doesn't look like a linear equation to me. No, because it's a recurrence relation. Basically, a recurrence relation is just telling you the relationship between one value and the next. All right, so if I just change its color so I can see it a little bit easier. All right, so this is one value, and so that's our previous value, let me just say. So we could say 20 plus 2 gives us our next value. Then 22 plus 2 gives us the following, and so on and so forth. So 24 plus 2. So we're basically adding 2 each time. All right, and you can see that happening there. Now for the rule, all right, this is looking more like a linear equation. All right, so remember your linear equation is y equals mx plus c. Sorry, I just need to turn my phone off. All right. But it doesn't look like that. You're like, why are we introducing more letters? Why can't we just stick with y equals mx plus c? Why have we got vn equals v0 plus nd? I just don't get it. So in maths, unfortunately, they like to complicate things. And when we do statistics, you're going to end up seeing y equals a plus bx, I think it is, off the top of my head. All right, it just changes, but it's still a linear equation. So the vn is your y. All right, so I'm going to write that first. Now, we have, first of all, with our linear equation, we have the gradient, whereas this one, we've got our starting value. So it's just switched sides. All right, so your y-intercept, we can see here, is 20. All right, plus n times our common difference. So if I wrote it like that, it would be n times 2. Now, with algebra, we don't tend to write it like that. So 20 plus 2n, which is also the same as 2n plus 20. So you can kind of see how it relates to y equals mx plus c. We're just using different letters because in maths, why make things so straightforward? It's just complicating it a little bit. But as I said before, if you see a question where you've got to do a recurrence relation, the only things that change the initial value and the common difference. So you should be writing v0 equals and then figuring out the initial value. You should be writing vn plus 1 equals vn and then working out the common difference. The only thing is you might be using a letter other than v. V is common, A is common, B is common. You could have any letter, probably not N or D, but VA, very common. All right, so just be aware that other letters can be used, but it's the same thing. You just need to have your initial value and your common difference. All right, I'm just going to scroll and see. With arithmetic sequences, so the financial applications of arithmetic sequences is we could have simple interest, and which is an example of arithmetic growth. And we could have flat rate depreciation, which is an example of linear decay, and unit cost depreciation, which is another example of linear decay. So let's just quickly go through these examples here. Now, simple interest, so you're either going to have simple interest or compound interest. Compound interest is an example of a geometric sequence, whereas simple interest is an example of an arithmetic sequence. So simple, basically because we're going to go up by the same amount. So a fixed amount each time. So if you're got a, say an investment, and it's paying simple interest at a rate of 10%. So let's say you invested $100. So let me just write that down. So if we invested $100, 10% of that is $10. So basically every year it's going up by $10. So there's your initial investment and it just goes up by 10 each time. So with simple interest, it's the same amount. You're not getting interest on top of interest. Now, most investments and loans are examples of compound interest, but you still need to understand simple interest as well. All right, so it goes up by the same amount. Now, this simple interest formula, you can still use in units 3 and 4. You probably were introduced to it in unit 1 and 2, or even in year 10. So I equals P times R times T. So I is your interest earned after T years. P is your money borrowed or invested. So we tend to call that the principal. R is your annual rate of investment, and T is the length of time you borrow or invest. Now, you can use this formula, but with simple interest, it is, I don't want to say quite simple, but once you got your head around it, I probably wouldn't use this formula that much because it just makes sense, like I did here, just to calculate what 10% was and then add it on each time. And if I wanted to know how much interest was earned, I take my final amount, and subtract the initial amount. So I've earned $50 in interest. So when we do some questions on arithmetic sequences, hopefully you'll see, okay, I don't need to really use I equals P RT. And this can be transposed as well. So what I mean by that is you can rearrange that equation to solve for P, for R, for T, not just I. All right, now the two types of depreciation or examples of linear decay are flat rate depreciation and unit cost depreciation. So I just thought, well, what's a good example of flat rate depreciation? Probably not a car. I would say that would be an example of geometric decay, but we're going to look at it anyway. So let's say you bought a car and it depreciates by $1,000 each year. So it's the same amount each year. So let's say I bought that car for $50,000 and after 1 year it's now $49,000, and then after 2 years it's $48,000, and so on. So it's going down by the same amount each year. Most cars don't work that way, because they say if you buy a brand new car, as soon as you drive out of that car sales place, I can't even think what they're called, your car is depreciated by a lot. All right, if it starts at zero, as soon as you start driving it, it has depreciated significantly. And obviously other things depreciate your car. But flat rate depreciation, just think same amount each year. It's an example of an arithmetic sequence. Unit cost depreciation, so thinking of an example of a coffee machine. So let's say you owned your own cafe and you depreciated your coffee machine, because let's not get too complicated into how the tax system works, but you can claim the depreciation of items that you use to earn an income. So an example would be a coffee machine. So instead of depreciating with flat rate, so let's say we bought this coffee machine for, I don't know, $1,000 and it depreciated by $100 a year, that would be flat rate depreciation. Unit cost is based on how many times we use the machine. All right, so here, let's say it was 50 cents for every coffee made. So it's a unit cost depreciation. So it's not done per year, it's done per use. So coffee machine is a good example. So every time you make a coffee, that coffee machine depreciates in value. So the word depreciate means goes down in value. Appreciate is go up in value. Most things depreciate. You could also have a coffee machine that is an example of flat rate depreciation. Doesn't have to be unit cost. And you could have a car that is also unit cost, so maybe it depreciates per kilometre driven as opposed to time. So flat rate depreciation is usually given by time, and unit cost is per use. All right, that's the main difference between the two. All right, so that's arithmetic sequences in a nutshell. Let's have a look and compare it to geometric sequences. So if you're using these posters, I strongly encourage you to have them side by side. So this first one, where we're kind of just looking at sequences, not the financial application of it, I would have it next to, if we can flick over, this first page. All right, so see how they're set out quite similar? All right, if you had them next to each other, it's got a quick, all right, which one's which? All right, is it arithmetic or is it geometric? Until you get the hang of it, because eventually you will know the difference between the two. All right, geometric sequences, slightly different. Instead of adding a common difference, we are now multiplying by a common factor. All right, so this one here, we are multiplying by 4. Now, the difference between arithmetic and geometric, all right, so here we add and we can subtract. So geometric, you might think, oh, why are we still just multiplying? Why aren't we dividing? All right, so if we do that, it just complicates things. We'd like to have a common ratio. So our common ratio, oops, come on, is 0.5 here, and for this one, it's 3. If we started dividing, then it wouldn't be called a common ratio anymore. So it's just easier to say, all right, we're multiplying. Now, multiplying is the same, and I'm going to get a little bit tricky here. Multiplying is the same as dividing, dividing is the same as multiplying by the reciprocal. So if I was to say, all right, if I wanted to divide by Actually, no, I don't want to divide by half. I want to divide by 2. All right, if I wanted to divide something by 2, remember when you did fractions and you learnt the phrase keep, change, flip? All right, it's the same rationale here. All right, that's all you were doing when you were dividing fractions. You were changing the division to a multiply and flipping, or taking the reciprocal of whatever you were dividing by. So we changed that division to a multiply and we multiply by the reciprocal. We've flipped that. So 2 is the same as 2 over 1. So if I flip it, it becomes 1/2. So dividing by 2 is the same as multiplying by 1/2. So if we just had a quick example, in case you don't believe me. So 10 divided by 2, we know is 5. 10 times 1/2. So remember, we can say that's 10 over 1. So 10 times 1 over 1 times 2. All right, so we still get 5. So geometric sequences, it's always multiplying. We don't have a division. When you do matrices and you're looking at scalar multiplication, again, you don't divide, and you'll also see it in statistics. So when you're multiplying, just remember, yeah, we tend to not divide, we just multiply by the reciprocal. So this one here, you can say, oh, we're halving each time. We're dividing by 2, which you can clearly see. But our common, if we had to state what our common ratio is, all right, we're multiplying by that reciprocal. All right, so the reciprocal of 2, or if we flipped 2, is 1/2. All right, so hopefully I didn't overly complicate that. Now, if your common ratio is less than 1, it's decreasing. All right, that's what we've got written there. It's decreasing. It's this red graph here that is now green, that I've painted in green. So let's just undo that so we can keep it red. But that's the one I meant. Now, if it's increasing, your common ratio is greater than 1. All right, so it's getting bigger each time. So that's the blue example. So you can see them both there. That's the graph. So these are examples of exponential growth or exponential decay. All right, so we tend to call it just geometric growth or geometric decay, but it's also exponential growth, exponential decay. A good example of geometric growth is COVID. So, and if you've done biology, you probably learnt about cell division. So all right, slight interruption, phone just rang. I think I was talking about COVID. So when we are in lockdown and, you know, we're all thinking, oh my gosh, there's been one case in like Queensland or something. And you're thinking, oh my gosh, this is going to go crazy. And others are probably thinking, but it's only 1. But 1 then becomes 5, and then 5 becomes 100, and then 100 can become 2,000. So you think it starts, so exponential growth or geometric growth, you start off very small. So just make sure I've got the pen. If you've got just a few cases, but it didn't take for long at all for it to get very rapid. All right, and that's the same as bacteria growing. That's why we have to live in a clean house and stay clean and everything and healthy, because bacteria or cells, they grow very, very rapidly. All right, and then you've got decay. Oh my gosh, I can't think of an example of a decay other than, you know, something depreciating in value. So we'll have a look at that in a sec. So let's use the car as an example. I know we use the car as arithmetic, but it could be geometric as well. So here's your car at a very high price. Probably not there on your graph though, but let's just say it started there at 50,000 and it drops at a sharp rate. All right, as soon as you leave that car yard, it is going to drop in value significantly, but obviously it's never going to reach 0. So it gets closer and closer to a low value. But like my car, I bought, I think it's now 11 years old. I think when I bought it, it was about 35,000 brand new. I could probably sell it now for about $10,000. And it's probably been about that price for a few years now. And if I waited a few more years, it's probably only going to go down by $1,000 or $2,000. So kind of, you know, flattens out. It's never going to reach 0 unless it was a write-off. So even in 10 years time, it's not going to be $0. you know, even in 20 years' time, I could sell it for parts. All right, it's still going to be worth something. It's not going to actually approach zero. So there's an example of geometric decay. And there's your graphs, what each one of them looks like. So that's why it's a good idea to have the arithmetic and geometric next to each other, so you can compare things like what the sequences look like. You can compare what the graphs look like. And then down at the bottom, we've got the recurrence relation and the rules, which are also different. So here we've got, so this is just for your graphs. All right, so it's increasing when your common ratio is greater than 1, decreasing when it's between 0 and 1. Now, if it was less than 0, so if it was negative, you're actually going to end up with a zigzaggy graph. If it was 1, it doesn't change because we're multiplying by 1 each time. So if you're thinking, why is it always greater than 1 and less than 1? It's because if it was 1, it would stay the same. All right, you multiply any number by 1, it's still that number. So 50 times 1, it's still 50. 98 times 1, still 98. And we don't have 0 as a common ratio because multiplying by 0 will give you 0. All right, so let's have a look at the recurrence relation. So again, you've still got this V0 business, and now we've got the starting value also means the initial value. I just realized it said initial value on the arithmetic sequence, but same thing. And your common ratio. So they're the two things that will change for a recurrence relation. So make sure you remember that. All right, so same as before, V0, your starting value, Vn plus 1 equals whatever your common ratio is times Vn. We're going to do some examples probably in a different video because I want to keep these videos quite short of questions using arithmetic and geometric sequences. All right, then we've got our rule. All right, so this is an example of an exponential equation, but most of you probably haven't had experience in exponential equations, so I won't worry about that. So we've got Vn equals, so the only things that will need replacing are your common ratio and your V0. So everything else stays there. So when I see these types of questions on an exam, I'm like, these should be gimme marks, all right? Because it's just a matter of putting in your starting value and your common ratio. Or if it was arithmetic sequence, it's just a matter of putting in your starting value and your common difference. All right. This part here in this little box, so because you're mostly applying this to financial, I thought I'd put this here because your common ratio, all right, as soon as we start introducing financial, you're going to have to work it out what your common ratio is. So R is your interest rate. When we go to the next page, we'll do more of this. So R is your interest rate. So it's going to be 1 plus if it's growing. If it's decaying, it's going to be 1 minus. And the reason for that is, maybe I'll wait until we do some questions, might be a bit easier. So if it's growing by R%, so let's say if it was growing by 5%, it would be 1 plus 5 over 100. So it'll end up being 1.05. So it's greater than 1, it's growth. Then less than 1, it's decay. So if it was decaying by 5% each year, it'll be 1 minus 5 over 100, so 0.95. So think of it with your phone battery. If you lost 5% in battery, you've got 95% left, right? So 0.95. All right, so the financial applications of geometric sequences. So again, good to have these side by side. All right, so I would have it next to this page because arithmetic is simple interest, geometric is compound interest. All right, so good to have that quick comparison. All right, so basically compound interest means it's compounding. It's interest on top of interest. So an example of geometric growth is compound interest, and you could have either an investment or a loan. All right, both of them are examples of geometric growth. So our principal, all right, we use the word principal. It's also our starting value. So in finance, we usually say the starting amount is your principal amount. So it's the same recurrence relation as on the previous page. You've got your principal and you've got your R value, your common ratio, but because we're applying it to financial, you're going to be given an interest rate. So if it was an investment, all right, you just put your interest rate in there and work out what your common ratio is. So this is very important that you understand that part of it. All right, with your rule, all right, same as before, and you're probably thinking, no, it doesn't look anything like that. So remember, R is this, okay? So R is 1 plus little r over 100. So capital R is your common ratio, little r is your interest rate. Just to complicate things, why not? All right, so this is still your R, all right? And then we've got that little n to the power of n. All right, so I'm just going to read what this example means. Loans and investments with a bank are mostly examples of compound interest. This means the value of the loan or investment increases by a different amount each year, an example of geometric growth. All right, so an example is loans and investments. All right, reducing balance depreciation. So looking at the depreciation part now. This is again why it's important to have these side by side, because you might have a question that says using a certain type of depreciation, and you need to know whether that depreciation is an example of geometric or an example of arithmetic. All right, so arithmetic, remember, we'll just go down, is flat rate depreciation and unit cost depreciation, whereas geometric is reducing balance depreciation. All right, so good to have them side by side so we can see that. All right, so I use the example of a computer. All right, if we get a laptop computer, it depreciates in value. So we all usually have our own laptop, and let's say we bought it for $2,000. We got top of the range, a MacBook, whatever. All right, I need it for, high school, so I've used it from year 7 to 12. At the end of year 12, I am not selling that laptop for $2,000. All right, I'm probably selling it for less than half that. All right, if you've had it for 6 years, it's not going to be worth the same that you paid for it, because why would someone want a 6-year-old computer when they could go out and buy a new one? Now, there are some things that do go up in value. Houses is probably the biggest one that does go up in value. And on my TikTok For You page, I've been seeing a lot of Birkin bags, and oh my gosh, it's just ridiculous. So they're an example of something that goes up in value, but we don't need to go up into the handbags. But most things depreciate. All right, if you went out and bought a handbag from Mimco, it's also going to depreciate. It's no Hermes bag. All right, it's going to depreciate in value. So geometric decay, reducing balance depreciation. It's the only example we're going to really look at in general maths. You still have the same recurrence relation. There's your initial value. All right, so we've seen the phrase initial value be used. We've seen the phrase starting value be used, and also principal. They all mean the same thing. Okay, so just remember that. They all mean the same thing. And then we've got our common ratio, but this time it's 1 minus because it's going down in value. All right, and I'll show you an example of this in a second, maybe using the laptop. All right, and before I do that, let's just have a quick look at the rule. So there's your rule. Remember, that is your R. The main thing is we've got a minus there, whereas if we were doing growth, it's a plus. All right, so let's say I bought my laptop for $2,000. All right, and just to make things easy, sorry, phone rang again. So $2,000 laptop, make it easier. Let's just say it depreciates by 10% each. Reducing balance. So it's depreciating at a rate of 10% each year. So this is not, so 10% of 2,000 is $200. It's not depreciating $200 each year. All right, because that would be flat rate depreciation. Reducing balance depreciation is 10%, and that is going to change each year. My common ratio. Now, let's think about what that actually would be. Think of your phone battery. If you lost 10%, how much would you have left? 90%, yeah? You got 90%. So you've got 90% of this value, 2,000 each year. Well, it's going to change because it changes each year. So that's where that is used to calculate. So 1 minus 10 over 100 is 0.9. All right, so as a decimal, it's 0.9 or 90%. So on the calculator, we're going to do 90% of 2,000. All right, I don't have the calculator here to quickly do that, but I can do it. It's going to be 1,800. All right, so 1,800. So the first one is going to be 200, but then we're going to multiply that 1,800 by 0.9, and I'm just going to do it on my calculator next to me. Probably should know what that is on top of my head, but don't want to get anything wrong, you know. All right, so then it goes to 1620, and then we can do that again. All right, so I'm taking 90% of it each time, and you can see how it changes. All right, and then it will keep going. So it's not going down by the same amount each time. I'm just going to write the last amount here. So now, good thing also with financial, just as a reminder, on my calculator it said 0.2, but let's not be fancy cafes. All right, it is 20 cents. If you left that as 0.2 in an exam, you would not get that question right. All right, we're not a fancy cafe. We do not write 0.2. We got to write it to 2 decimal places. So it's 20 cents. All right, even though it means the same thing, in finance, we have to have 2 decimal places. All right, so I think that's probably enough. All right, so sticking those into your bound book I think would be good. All right, just have it as a quick reference. In a separate video, we'll go through some questions. All right, bye.